3. New functions from old functions, or differing techniques to obtain, at least at the beginning, there are 4 techniques, to obtain new functions from old functions. We'll then be defining so I'll tell you these first 4. So the first 4 are translations, moving in a rigid motion, right, left, up, down. Reflections, so where I look in a mirror at the object and reflect about, in this case, maybe the x-axis or y-axis. So I just sort of rotate the image about a particular axis. The only 2 axes that we're going to be, well, there are 3 of them. We'll be looking at 2 lines, the axes, the x and y axes, and we'll be looking at reflection about a particular point, in this case, just the origin. We'll also be looking at scaling. That's where you either zoom in or zoom out, stretching either the x-axis or shrinking the x-axis, or stretching the y-axis or shrinking the y-axis. That's scaling. Now rotations, I guess we won't actually do rotations. Rotations are, will be discussed in your Math 262 class. So no, they won't. I am sorry. I forgot about that. Rotations were discussed in your Math 259, Math 260 class. Rotations were discussed. Actually, also translation, reflection, and scalings were discussed in your intermediate algebra class, but we're going to discuss them again. And rotations were discussed in your pre-calculus class. I don't think we'll actually discuss rotations here. In addition to that, I'll also be able to add 2 functions, and I'll define them point-wise. Multiply a function by a scalar, a number. From there, we'll define other sort of operations involving those 2 operations. And substitution, which in functional notation is known as composition. Okay, so excuse me. Okay, so let me first discuss translations. Before I do that, let me give you some notation that will be useful when discussing things of this type. So let y equal f of x, let that be the original function that we're looking at. And somehow we want to do something to that function. And so I have here, well, our original function, y equal f of x. I'll assume that h here is greater than 0 and k is greater than 0. So I can make some definite statements about the direction. So that I can tell you if I'm, stretching or shrinking something. So let me make definite statements. And so let me just assume that h, k are greater than 0 and m is greater than 1. So first, let me discuss translations. And so I'll give you the transformation first, and then what results from that transformation. So, oh, well, that's cool. 43. That was a very, okay, so sorry about that. Okay, so I will discuss a transformation and then the result of that particular transformation. So I will replace x by x plus h. That will result in translating h in the negative x direction. So if I add h, I will translate in the negative x direction by a factor of h. Well, a negative, if I go in a negative x direction, then that just means, well, I'll be going in the negative x direction is to my left. And so the negative x direction is to my left. Therefore, I'll be translating this to the left. And so if I replace x by x plus h, I'll translate my original function by h units to the left. Similarly, if I replace x by x minus h, then I will translate by h units to the right. I'm going in the opposite direction. Now, let's replace y by y plus k. Again, just remember, this is a rule. Math is backwards. So if I add, just like last time, when I added h to x, I went h units in the negative x direction. Now, when I add k to y, I will go k units in the negative y direction. Well, negative y, that's going down. And so I'll translate my original function by k units down. Now, let's replace y here by y minus k. And so I will translate my original function k units up. Okay. So notice, in general, you look at the sign of whatever you're doing, or if you're adding or subtracting, and you go in the opposite direction. And so if you add, you go in the negative direction. If you subtract, you go in the positive direction. Math is backwards. That will then give you the correct translation. Now let's consider reflections. Let us replace x by negative x. Well, since I'm doing something to x and math is backwards, then I'll reflect about the y-axis. And so I'll reflect y equaling f of x by about the y-axis. If I replace y by negative y, then I'll reflect about the x-axis. Math is backwards. Now, let's do scalings. And so I am going to replace x by x over m. So you replace x by, let's say, x over 2. If you do that, if you're dividing, then what you do is you multiply your x-axis by a factor of 2. And so you would, if you replaced x by x over 2, then you would stretch your x-axis by a factor of 2. You would double, you would change your scaling by x over m. Then I will stretch. Notice, since I'm dividing by m, I will stretch. Next, let's replace x here by mx. Well, if I do that, then I'm going to compress. I'll shrink my x-axis by a factor of m. Next, if I replace y by y over m, then I'm going to stretch the y-axis by a factor of m. And if I replace y by my, I will compress the y-axis by a factor of m. So that discusses if we started with some function, y equal f of x, then I can translate. I can move to the right, left, up, down by adding or subtracting from x a particular, so let's say h, and add or subtract to y some constant, let's say k. I can reflect about an axis. If I replace x by negative x, I'll reflect about the y-axis, y by negative y, reflect about the x-axis. If I replace x, if I multiply by a scalar, all x's are replaced by some scalar multiple of x, then I will either stretch or shrink the x-axis. If the factor is greater than 1, I'll shrink it. If it's less than 1, I'll stretch it. And similarly with the y-axis, if we replace all y's by some scalar multiple times y, then I will shrink the graph by the factor. If that factor is greater than 1, and I will stretch it if that factor is less than 1. Okay, so next, I can now construct new functions, simpler ones, by just doing algebraic operations to them. And so I can start with maybe some simple function, the identity function, and get some algebraic function by adding, subtracting, multiplying these functions, by doing scalar multiplications of them, and doing combinations of those. If I do it a finite amount of time, I'll get a algebraic function. So let me define those types of operations that I can do to construct a algebraic function. And so let me give you the algebra of functions. So first, before we even talk about that, let me tell you how to determine if two functions are equal to each other. So the equality of functions, f equal g. So f is equal to g if, and I guess I should say this before I continue. Whenever we give a definition in mathematics, we always give it saying the word if. So I always say f is equal to g if these conditions hold. But we really don't mean the word if. We mean the word if and only if. So we mean that this statement is equivalent to the other statement. So even though we're saying if, it's really an if and only if. It's an equivalence that this notation is equivalent to whatever conditions we give. So just note, and this is not me, it's not one or two people, it's everyone. So it's every mathematical definition that you look at. We always say if, but it is understood that when we are doing a definition, the if means if and only if, means equivalence. Okay, so let me continue. That was an aside so that you could you could understand what I mean by f. So f is equal to g if the domain of f is equal to domain of g. and f of x is equal to g of x for all x in the domain of f. Or I could say domain g because they're the same. So when do we say that two functions are equal? Well, two functions are equal if they equal everywhere that they're defined. And they're defined in exactly the same places. And so, yeah, that's certainly a common sense idea of what it means for two things to be the same, for two functions to be equal. So next, let's define the addition of two functions. So suppose I have two functions, f and g. I'll define a new function, f plus g, as follows. I will define it pointwise. Actually, all of these definitions will be defined pointwise. And so f plus g evaluated at x will just be f of x plus g of x, where the domain of f plus g is defined as equaling the domain of f intersect the domain of g. Next, let's define scalar multiplication. So let C be some number, 23. And let f be some function, x squared. I'll define what we mean by 23x squared. Well, it's going to be obvious. We just mean that it's 23x squared. And so we define it pointwise. So some constant c times the function f evaluated at x is defined as that constant c times f evaluated at x, where the domain of cf is just equal to the domain of f. Let me define the additive identity. And so the additive identity, 0, the 0 function. So usually our notation is just 0. It looks like 0. But really, we mean that it's a function. It is a function such that at every point, it's just equal to 0. So 0 of x is just equal to the function 0 of x is equal to 0 for every x. And you really have, it's your choice to figure out what the domain of that is. It'll be different depending upon the situation that you're looking at. But it'll usually be, usually we don't specify the domain because in the context, it's obvious for the 0 function. The additive inverse. The additive inverse, denoted by this minus sign in front of f. The additive inverse of the function f, denoted by minus f, is the scalar multiplication of the number -1 times f. We've already defined scalar multiplication up here. So we know what -1 times f is. Next, multiplication. And so suppose I have two functions, f and g. I will define scalar multiplication of them. And so, again, I'll just do this pointwise. And so f times g evaluated at x is just equal to f of x times g of x, where the domain of f times g is just the domain of f intersect the domain of g. And of course, this makes sense, just like before. Where could you define the multiplication two functions? Well, you can only define two functions together where they're both defined. Obviously, you can't, if f is not defined at a particular point, then you can't plug in x here for f. And so you must have that both f and g are defined in order for their product to be defined. So this is the obvious sort of definite domain that you should define. And well, we do define it that way. Next, the multiplicative identity, the one function. So just like the zero function, the one function is defined as equaling 1 for all x. Next, the multiplicative inverse. So the multiplicative inverse of the function g is defined as 1 over g. Please note, maybe I should. This is not the same. So when you had like 1/2 and 2 to the negative 1, the notation was that those were the same. For functions, that's not those are two separate notations. So it turns out that you can't notate a multiplicative inverse with this superscript. And that's because, well, there is another multiplicative inverse, but that involves composition. This would be called the inverse function. That's the notation. Okay, so that's just sort of a note. So the multiplicative inverse of g, denoted by 1 over g, is defined again point-wise. So 1 over g evaluated x is just equal to 1 divided by g of x, where the domain of 1 over x, the domain of 1 over g is the domain of g, take away, so I'm doing this set subtraction, so take away the kernel of g, where the kernel of g is the set of all x's in the domain of g such that g of x is equal to 0. What this means is that you don't want to divide by 0. So if I define 1 over g of x, well, g has to be defined at x and don't divide by 0. So that's all I'm saying. How do you define 1 over g? Well, obviously g has to be defined at that point, x, and you cannot be divided by 0, so g can't be 0 at that particular value of x. So let me actually write this out explicitly. So the domain of 1 over g is the set of all x in the domain of g such that g of x is not equal to 0. So again, the only way you can really define 1 over g of x is if x is in the domain of g, so that g of x makes sense, and g of x is not 0, otherwise you can't divide by 0. So if g of x were 0, then you'd be trying to divide by 0, and you don't want to do that. So now let me combine the definitions of multiplication and the multiplicative reciprocal to get, well, division. And so the division of two functions. So the division of the two functions, f and g, so f divided by g, is defined as f times the multiplicative inverse of g, where the domain of f divided by g is the domain of f intersect the domain of g, take away the kernel of g. So again, f divided by g will be defined pointwise if, well, x is defined, is if f is defined for that particular value of x, and g is defined for that particular value of x, and g is not 0 for that particular value of x, so I'm not dividing by 0. So with these, well, I guess the only thing I didn't define, I should have, I guess, defined exponentiation, which is really a notation. But there's a reason why, because I need to define the inverse function of that so I can take roots. But if I did define exponentiation, you know, if I defined f to the power n, which is f times f times f, n times, and I define the nth root of f, which is just the inverse function of this. Then with the above operations, if you start with the scalars being the real numbers and a function being, say, the identity function.
That's actually n/1.
Identity function just takes x to x. If you do a finite number of operations involving this, then we'll obtain what are called algebraic functions. Okay. Ooh, didn't want that. Let's get rid of that. Okay, so let me give you some properties for
this is calculus.
These operations.
I would expect x.
Here, wait 1 second.
This is how you have to see exponents. Is that
I can hear something in the background. Well, and I wonder if someone's talking to me. But let's just see. Oh, okay, that's really low. Let me mute that in case that person just accidentally has their mic on. Okay. So I muted you just because I could hear a very small background noise. Okay, so, but if you're actually trying to ask me a question, just turn your mic back on it and turn the volume back up so I can hear you. Okay, so field properties. So it turns out that these operations that I've defined will actually make these functions satisfy the same properties that the rational numbers satisfy. So they sort of act like rational functions. And that's why we are able to discuss rational functions. And the rational functions really looked like rational numbers because they satisfy the same properties. Except for there's the completeness properties that are somewhat different. But any of the algebraic sort of field properties, they all satisfy the same things. So you would you notice that the arithmetic that you do with rational functions and the arithmetic that you do with rational expressions, rational functions, were always the same. So let me give you the field properties. First, the closure property for addition. Well, if f and g are functions, then f plus g is also a function. Next, the closure property for multiplication. If f and g are functions, then f times g is also a function. The commutative property for addition. So suppose here that f and g are functions, then f plus g is the same as g plus f. the commutative property for multiplication. Again, suppose that f and g are functions, then f times g is the same as g times f. The associative property for addition. F plus g added to h is the same as f added to the sum g plus h. The associative property for, the associative property for multiplication. If f, g, and h are functions, then f times g multiplied by h is the same as f multiplying the product of g and h. Next, the existence of an additive identity. And so 0, as we said before, the 0 function is the additive identity for this field of functions. So f plus 0 is just f. For any function f, f plus 0 is equal to f. And so I have that this is a right additive identity. And by commutativity for addition, we have that the 0 function plus any function f is just equal to the original function f. We also have the existence of a multiplicative identity. So for any function f, f times the multiplicative identity, the 1 function, is equal to f. And so the 1 function is a right multiplicative identity by the fact that multiplication of functions is commutative. I have that it's also a left multiplicative identity, that the 1 function is also a left multiplicative identity. The existence of an additive inverse. If f is any function, then there exists the additive inverse of f, denoted here by negative f, such that f plus negative f plus its additive inverse is equal to the additive identity, the 0 function. And so we have that this is a right additive inverse due to the fact that, well, the addition of 2 functions is commutative. Then it is also a left additive inverse. And henceforth, we just call it an additive inverse. The existence of a multiplicative inverse. If f is not equal to 0, then there exists a multiplicative inverse of f, denoted by 1 over f, such that f times its multiplicative inverse is equal to the multiplicative identity. And so 1 over f is a right multiplicative inverse. Since multiplication is commutative, then it is also a left multiplicative inverse. Therefore, we call this just a multiplicative inverse of the function f. Lastly, multiplication distributes over addition. And so function multiplication distributes over function addition. And so I have that f, some function f, times the sum of two functions, g and f, is equal to the sum of the product of the two functions, f times g, plus f times h. Not only do these satisfy the field properties, so they act like rational numbers, they also satisfy the vector space properties. So they act like vectors. So in previous classes, when you talked about vectors, you thought that, well, a vector is that it has some origin, some place that it starts, and it has, well, it has some direction, and it also has some sort of length. Well, it turns out that a direction and a length aren't that important. Just the algebraic properties, where you can add two vectors and get a third vector, and you can take a vector and stretch it. Those are the two important facts, the algebraic facts. Length gives us another important aspect of vectors called a normed vector space. And a direction is also important. That gives us what's called an inner product space. But a vector space, which is more primitive than those, only involves the algebraic properties of a vector. So just think of a vector as something where you can add two vectors. So let's say this is W. And you get something new, a new vector. Or you start with some vector and you can stretch it. Or, well, actually, if a is greater than 1, then you stretch it and make it longer. If it's less than 1, then you shrinks it, it's less than the vector. And if it's negative, well, then it goes in the opposite direction. But that's really the important properties that make up a vector space. The important properties of vector that make up a vector space is just that you can add in two vectors and do scalar multiplication. So it turns out that, well, with these functions, you can add functions and you can scalar multiply. And so it turns out that, well, these functions, this function space, is actually a vector space. And so a vector space of functions, which turn out to be very important because those sort of ideas are important, turn out to be central to the concept of a derivative. And so that will be just sort of hinted at during the next week or 2 weeks or so, actually probably almost 3 weeks, the next 2 to 3 weeks, where I'm going to hint and, but I won't delve too much into it. The fact that this idea of function can be thought of as vectors is sort of central to the concept of the idea of a derivative. It will be more evident when you do derivatives in dimensions in your Calculus 3 class. So in your Calculus 3 class, it'll be crucial that you really discuss the concept of a vector space, but so that you see where everything is headed, I will at least give you some hints about that. So that you're not sort of broadsided in later courses. So I'll at least give you a little bit of hints and a little bit of backgrounds. So the vector space properties. First, the closure property for addition, just like before. If f and g are functions, then f plus g is a function. The closure property for scalar multiplication. So in this case, our two operations will only be the addition of two functions and the scalar multiplication. If you remember when I drew that picture a few seconds ago, I was able to add two vectors and I was able to stretch a vector. But I really wasn't able to, multiply two vectors. If you have this vector and you have this vector, how do you multiply them? I don't know. And so I just define scalar multiplication because I can do that. So the closure property for scalar multiplication. Let C be a scalar. A scalar is just a fancy name for a number. So let C be a number. Usually a number will be a member of a field, such as the field of rational numbers. Or it could be, well, something more primitive, like a ring or something. So it could be like maybe some integers or something. In which case, usually we give them different names than vector spaces. But just think of C as being a scale. Think of a scalar as just being a number. Most of the time, we'll just be dealing with real numbers. So the only numbers we're really concerned with, mostly in this course, even though sometimes we do complex numbers, but mostly in this course are real numbers. And hopefully by next week, I will discuss why we only consider real numbers and why we don't consider other things in calculus. Why don't we look at rational numbers? Why don't we look at integers? Why don't we do those sorts of things? Why do we only consider real numbers? Why don't we consider complex numbers? Why? And so for right now, just sort of take it that in this class, we'll really only be looking at real numbers. And there's a fundamental reason for that. Not that we're just lazy and we only want to do it for real numbers. There's really a fundamental reason why we only do real numbers. So let C be a scalar, let f be a function, then C times f is also a function. The commutative property for addition. So if f and g are functions, then f plus g is equal to g plus f, just like before. The associative property for addition. Let f, g, and h be functions. Then f plus g in parentheses plus h is equal to f plus in parentheses g plus h. The associative property for scalar multiplication. Let a and b be scalars, numbers. Let f be a function. Then a times, in parentheses, bf is equal to, in parentheses, a times b, in parentheses, times f. The existence of an additive identity. So there exists, and usually I'm lazy, and I will give a symbol, and this is a common symbol, this backwards E. So this backwards E represents there exist, and this sort of backward, like a euro type symbol, backwards euro symbol, denotes such that. And this sort of wedge symbol here denotes logical and. And actually, if you do it this way, then this represents logical or. So there exists the zero function such that f plus the additive identity is equal to the original function f. And we have that the zero function plus f is just equal to f. The existence of scalar multiplication identity. There exists a number 1, so this is a number. So there exists the number 1, so the usual number 1, such that 1 times f is just equal to f. The existence of an additive inverse. For every function f, there exists a function denoted by negative f, such that f plus the additive inverse of f is equal to the additive identity. And by commutativity, the additive inverse of f plus f is equal to the additive identity, the zero function. Scalar multiplication distributes over vector addition. And so let C be a number, a scalar. Let f and g be functions. Then C times, in parentheses, f plus g is equal to C times f plus C times g. Next, scalar multiplication distributes over scalar addition. Let A and B be numbers, scalars. Let f be a function. Then A plus B in parentheses times f is equal to AF plus BF. Okay, so those are the properties that specify that a set of functions given these algebraic operations along with some scalars, some numbers, will satisfy the properties of a vector space. So this set of functions can be thought of as a vector space as having the same properties as a vector, the same algebraic properties as a vector. Obviously, they don't really have a direction or a length, but they have the algebraic operations of a vector. Next, let me discuss composition. So composition is just a fancy term for substitution. It is substitution utilizing functional notation. So if I do substitution and I use functional notation, we call that operation composition. So suppose I have here some function f that maps the point X to the point. Okay, I just want to check that I don't have an echo here. Showing audio. Yes, yes. Good, good. Okay, thank you. I was just paranoid that once this happens, other horrible things happen. Okay, so I apologize for getting kicked out of the internet for a few seconds. Okay, so let me discuss composition. Okay, so again, composition really is just substitution. So the composition of functions. So given functions f from the set x into the set y, and the function g from the set y into the set z, we define the composition of g and f as follows. G composed with f is just the set of all ordered pairs x comma z such that the ordered pair x comma y is in f, and the ordered pair y comma z is in G. So this is utilizing our ordered pair definition of function. So I have here that if f here maps x to y, x into y, and if g maps y into z, then the rule taking x into z is denoted by G composed with F. This is actually called a commutative diagram. This diagram here, which helps you to understand what's going on, is called a commutative diagram. We saw these yesterday. And in a commutative diagram, if you start somewhere and you go in any path and end at the same place, then where you start, if you start at the same place, then you have to end at the same place. And so any path that ends at the same place. No. Okay. Gives the same values. So I see here, if I start here, I go along this path, I end at Z. So that means that if I take X, and if I start here, I also end at Z. And so if I go from X, and let's say I move along this path, and give me a Y, then this Y gives me some Z. Then going along this path, and this was F and G gave me those. Then going along this path here, starting from X and ending at Z, gives me this, has to give me the same values. So that says that F, that G composed with F at X must equal, well, This is F. I take F, evaluate at X. Then I take that, whatever I got here, which I called Y, which is F of X, and it gives me some Z. So it has to be that G composed with F at X is just G evaluated at F of X. Looking at this diagram. Maybe I'll leave this here for. Okay, so note the following, that G composed with F is not the same as, I'm sorry, that F composed with G is not the same as G composed with F. So it turns out that you can't commute these. So this is not commutative. So it almost acts like multiplication, but it does not commute. So it's a weird sort of multiplication. So please note that F composed with G is read there. That F composed with G, F circle G, is read F of G. And G with this little circle F, so G circle F, is read G of F, or G composed with F. So using this sort of idea that I wrote here, let me write this definition again. So composition. So let G, oh, and I wrote it the other way, so it looks nicer. So let G map X to Z. Let F map Z into F. Okay, let me start this again. So let G map the set X into the set Z. Let F map the set Z into the set Y. So let these be mappings, rules. Then the rule defined by F composed with G at X, which is equal to F evaluated at G of X, with the domain of F composed with G equaling the set of all X's, such that X in the domain of G is such that G of X is in the domain of F. This is called the composition of F with G. So again, composition is just substitution using functional notation. And so if G maps X to Z and F maps Z to Y, then the mapping of X to Y is denoted by F composed with G. Note the following, that if the rule F, the function, F mapping X, the set X into the set Y is surjective, also called onto, and if the function G mapping the set Y into the set Z is surjective, then G composed with F mapping the set X into the set Z is also surjective. So if f maps x onto y, g maps y onto z, then g composed with f maps x onto z. Also, note that if f maps x into y is injective, 1-to-1, and if g maps the set y into the set z is also injective, then g composed with f mapping the set x into the set z is also injective. So an injective function composed with an injective function is also injective. Lastly, if f mapping the set x into the set y is bijective, and g mapping the set y into the set z is bijective, then f composed with g, then g composed with f mapping x into z is bijective. Sometimes we call a bijective function a 1-to-1 correspondence. So in grade school, when they first discussed bijective functions, they called them 1-to-1 correspondence. Actually, when they did, the very first time they discussed bijective functions, 1-to-1 correspondence is in preschool. They actually do it in preschool. Okay. 1 second. Oops. Okay, so. Oh, good. Let me do. Hey, wait, I've got to. Okay, so let me do this. So on page 43, problems 9 through 24, graph the function by hand, not by plotting points, but by starting with the graph of one of the standard functions, the power functions that we discussed the other day. So graph the function by hand, not by plotting points, but by starting with the graph of one of the standard functions given in section 1.2, and then applying the appropriate transformations. And so we have here problem number 10, y is equal to x minus 3 squared. So we see that this is a translation. And so this will be a translation. What we've done is we've replaced x by x minus 3. Oh, you stop. So I replaced x here by x minus 3 in the function of y equaling x squared. So if I take y equal x squared, and if I replace x by x minus 3, well, then I get the function here, y equaling x minus 3 squared. So this is just a translation. Well, actually, I should see it here. This is a translation. So I'm going to translate y equaling f of y equaling x squared by 3 units. Well, let's see. I'm taking x and replacing x by x minus 3. And so that's in the x direction. Well, in the x direction, I'm either go right or left. I'm subtracting. So the negative y direction is to my left. Math is backwards. Therefore, I'm going to translate 3 units to the right. Okay. And so let's do this. Okay. So let's start out with y equals x squared. So this is the graph of y equals x squared. It's a parabola. It's the standard sort of parabola that we did last class. And now I want to translate this 3 units to the right. So I'm going to take this and just move 3 units. Okay, good. So, I don't know, let's say this is 1, 2, 3. So, it doesn't quite look like the same function. Let's not make it as wide. Not too bad. Okay, so just there. Okay, so this is 3. So I've taken the origin, I've taken this point here and moved it 3 units over. I sort of put a big point there because I missed the axes. So I'm just sort of trying to obscure the fact that I did that by making a big splotch there. And so this is the graph of y equaling x minus 3 squared. So I'm just hiding my errors. Any questions about this? Now, of course, now it doesn't look like they overlap, but obviously they do. I just sort of, the way I've drawn it, doesn't look like they overlap, but they do. Okay, there are no questions about that. And let's do the next problem. Oh. I thought it might take more room than it does. Okay. In problems 31 through 32, find A, f plus g, B, f minus g, C, f times g, D, f divided by g. So this is another symbol for the division. I used, I guess, the line with 2 dots, well, 1 dot above, 1 dot below. But obviously, this is also another notation for division. And state their domains, where f of x is equal to radical 3 minus x, and g of x is equal to x squared minus 1. So let's do this. So part A, f plus g. Okay. In 1 second, actually, let's see if I can do this. Sorry, I'm trying to do more than one thing at one time. To answer someone's question and type in the answer and do this simultaneously. Okay, sorry. 1 second. Let me give the link to the other students. They want to know what the link is to the Zoom session. So trying to do that. I apologize for taking an extra second here to answer that. Okay. There you go. So let's apologize for taking that extra time to answer the other students. Okay, so let's do f plus g value at x. Well, f of x is equal to the square root of 3 minus x. And g of x is equal to x, the square root of x squared minus 1. So that's, well, f of x plus g of x. Now let's try to determine the domain of this function. So long as you don't simplify, it turns out that the domain of this function is the same as the domain that I gave previously when I defined addition. So, well, I don't want to take the square root of a negative number. So 3 minus x is greater than or equal to 0. And I don't want to take the square root of a negative number. So x squared minus 1 is greater than or equal to 0. So I have here that 3 is greater than or equal to x, adding x to both sides of an inequality. So x is less than or equal to 3. I also have that, well, I can factor x squared minus 1 as x minus 1 times x plus 1. X squared minus 1 is just the difference of squares. So I can use my special product formula to factor this. And so let's find my critical numbers. So let me determine my critical numbers. In this case, my critical numbers are, well, x equal 3 and x equal plus or minus 1. Okay, so let me put these on my number line. Actually, let me do this as 2 separate number lines. So let me do the fact that x, okay, there, that x is less than or equal to 3, and the fact that x minus 1 times x plus 1 is greater than or equal to 0. Okay, so let me do that. So, and let's do these separately. This would be an and. So if I look here, I have 3. Well, I want that x is less than or equal to 3. So I fill in the 3. And then it's less than or equal to, so I'll go in this direction. Oops. And so I have that x is less than or equal to 3. And, well, let's do the other one. I have here that x could either equal -1, that's a critical number, or +1, that's the other critical number. Let's pick a number greater than 1, let's say 2. So positive times positive is positive. Take a number between -1 and 1, let's say 0. And so negative times positive is negative. Take a number less than -1, let's say -2. Negative times negative is positive. We want this to be greater than or equal to 0. And so let's fill this out. So fill in each of these critical numbers. This is less than or equal to. And the plus sign, because it's, I'm sorry, it's greater than or equal to. So I fill in the plus of this. Okay, so in this region, my first function, f, is defined. In this second region here, well, my second function is defined. So I want both functions to be defined. So I want to find the overlap between them, the intersection between these two. And so for this one, x is always less than or equal to 3. And so I want that x is always less than or equal to 3. So we'll include this guy and include this guy up into 3. And so the overlap between these is going to be, well, here's -1, here's 1, and here's 3. So -1 is certainly less than 3. So it's inside this and inside that. 1 is also in here, and it's also less than 3. And 3 as well in here, and it's also in this guy. Okay, good. So now let's fill in the rest. Well, oops, just pointed. So this region here, x is less than -1, less than or equal to -1, are less than or equal to 3. And so this whole region here is in, why is it erasing and not picking this? Oh, that's just weird. Okay. Okay, let's see if it will do this at least. Why is that an eraser now? Now it's no longer an eraser. Okay. Having some mental problems with the computer. Okay. Voila. Okay. Next, if x is between 1 and 3, then it's less than or equal to 3, and it's greater than 1. So this region here is also included. And so the domain, maybe I should label this actually. This is the domain of f. this was, oh, come on. This was the domain of G. This is the domain of F intersect the domain of G. And so the domain of F plus G is the union of negative infinity to negative 1, union 1 to infinity to 3. So that's the domain of our function. Okay, good. Let's do part B. And I'll use the fact that the domains are the same, so I won't need to work nearly as much for the next parts. Actually, let me ask you before I go on, any questions about the domain? Any questions on how I determined the domain? Okay, so let me do part B. F minus G. Well, F minus G is just, F is the square root of 3 minus X. G is the square root of X squared minus 1. And so that's F minus G. And what's the domain? Well, the domain of F minus G is the same as the domain of F plus G. And so it's just negative infinity to negative 1, union 1 to 3. Let me do part C. So we took all the time in part A. Now the rest of this will go much swifter. So part C, F times G. And so F times G at X is just F, 3 minus X times G, X squared minus 1 in square root. And so that's F times G. Of course, you could put this all over one big square root if you want. And the domain is, well, actually, let me write this as the square root of 3 minus X times X minus 1 times X plus 1. And so let's find the domain of this function. First thing to do is to find the critical numbers. To find the critical numbers, well, I've already factored it out. And so the critical numbers in this case are just where what's inside the square root is equal to 0. So, well, obviously, well, maybe I should write this down first. For my domain, I do not want to take the square root of a negative number. So I want that this product here is greater than or equal to 0. And so the critical, let me determine my critical numbers. So then my critical numbers are 3 plus or minus 1. Let me draw a number line, place the critical numbers on my number line. Take a number greater than 3, 4, negative, positive, positive, negative. Take a number between 1 and 3, let's say 2, positive, positive, positive. Take a number between negative 1 and positive 1, let's say 0, positive, negative, positive, negative. Take a number less than negative 1, let's say negative 2, positive, negative, and negative is positive. We want this to be greater than or equal to 0, so we fill in anything that says a plus. Let's fill in the pluses. And it's less than or equal to, so I also fill in the critical numbers. And so the domain of f times g is negative infinity to negative 1 union 1 to 3. And of course, what you notice is that this is the same as before, because while the domain of f plus g, the domain of f minus g, and the domain of f times g are all the same. So obviously we should get the same answers. D. I want to find f over g at x. So this is, oops. So this is equal to f 3 minus x square root divided by g x squared minus 1 in square root. So this is equal to 3 minus x over x minus 1, x plus 1 in square root. Okay. Again, I can find the domain. Actually, I know it's everything. I know it's everything but the same as the domain of f times g. Take away the kernel of g. So that would just take away where g is 0, the critical numbers. So it would take away the 2 critical numbers. But maybe I will act as if I don't know that. So let me act as if I don't know that. That all I have to do is erase these 2 and put parentheses there. So let's find a domain. No, let's find a domain. So to find the domain, let's find the critical numbers. You will find that, well, people probably think at the end of this course, all we do is find critical numbers. So, and that's almost a true statement. You know, determine the critical numbers, or sometimes stated, you know, set first derivative set equal to 0. That's sort of 90% of this course. So determining critical numbers is almost 90% of the course. Okay, so let's determine my critical numbers. And so I'll set each of these equal to 0. So 3 minus x equals 0. So x is 3, and x minus 1 is 0. X plus 1 equals 0. So x is equal to plus or minus 1. So let me place these on my number line. I guess I'll need one more page. -1, 1, 3. Okay. Let's determine the signs. Actually, you'll find that signs are all the same as before. Let's take a number bigger than 3, 4, negative. Oh. So it's negative divided by positive, positive, negative. Take a number between 1 and 3, let's say 2. Positive, positive, positive is positive. Between -1 and 1, let's say 0. Positive divided by negative times positive is negative. Take a number less than -1, let's say -2. Positive, negative, negative is positive. We don't want to take the square root of a negative number. I should have said that this, obviously this is, we want this to be greater than or equal to 0. Actually, I need another page anyway, so I'm just adding another page. Okay. Let me just move this down, if I can. Oh, that's nice. Let me try to move this. There. Okay. So I want that this I should have stated this is greater than or equal to 0. That's how we find the domain. Even though I said it, I didn't write it down. But now I've got room, so I'll write it down. Okay, so there. We want it to be greater than or equal to 0, so I fill in the pluses. I want greater than or equal to 0, but I don't want to divide by 0. So note that you're dividing by 0 here. So at these critical numbers, the plus or minus 1, you're actually dividing by 0. So I don't want to have, to include the critical numbers, plus or minus 1. It's okay to include the critical number 3, because then you're not dividing by 0. 0 would be in the numerator at that critical point. And so let's fill in. Oops, I was filled in the wrong one. Let's fill in 3. I will not fill in 1 nor -1. So these are open. And so the domain of f divided by g is the union of the open interval, -infinity to -1, union the half open, half closed interval from 1 to 3. And that's your domain. It is just the previous domain where I've taken away the critical points plus or minus 1, which is the kernel of G. It's where you're dividing by the x squared minus the square root of x squared minus 1. So you don't want to divide by 0. And so you've got to take away those critical numbers at plus or minus 1. Okay. Let me do problem number 34, I guess. So similar, but not the same. In exercises 33 through 38, find the functions A, f composed with G, B, G composed with F, C, F composed with F, and D, G composed with G, and the domains. What we will note is that F composed with G is usually not the same as G composed with F. So we'll probably get differing answers for part A and part B. Problem 34. F of x is equal to x cubed minus 2. G of x is equal to 1 minus 4x. And so let's try to determine each of these. So A. F composed with G. Evaluate x. So composition, if you remember, is just substitution. So F composed with G. Wherever I see an x in the formula for F, I'm going to replace x here by the formula given by G. So wherever I see an x, here I'm going to replace x by 1 minus 4x. So in this formula, I'm going to replace this x by 1 minus 4x. So this is equal to replacing x by 1 minus 4x. 1 minus 4x quantity cubed minus 2. Now, I'm going to be lazy, and I'm not going to simplify this. Why? Well, because I'm lazy. And next, because, well, we're not doing anything with this. And so there's no reason to further simplify. If you're trying to do something like take, solve an equation or something, then you may have to simplify, but they're not asking me. They're just saying, what is F composed G? So, well, that's F composed G. I didn't simplify it, but that's fine. They're also asking, what's the domain? Well, in general, it's, you don't simplify to find domains. Because when you simplify, many operations in simplification involve changing the domain. And so even though in this case, we would not change the domain because we're just doing exponents and there's nothing in the operations that we're doing that changes domain. But in many times that we do things, we unconsciously, when in simplification, change the domain. So it's best not to simplify when determining domains. Here, this is just a polynomial. It's a cubic. And well, you can always, if I take a number, can I multiply it by 4? Sure. Can I subtract it from 1? Sure. Can I cube it? Yeah. Can I then subtract 2 from it? Sure. And so the domain is everything. So the domain of my function is all real numbers. Let's do part B, which is basically the same thing. It's just G composed with F at X. So here, wherever I see an X in the formula for G, I'm going to replace X by the formula given by F. So wherever I see an X, I'm going to replace X here by X cubed minus 3. So my answer will just be this, where I replace this X by X cubed minus 3. So it's 1 minus 4 times replace X by X cubed minus 3, X cubed minus 2. And that's your answer. Actually, it's easier to simplify this, but I'll leave it this way. The domain, but you notice that these are not going to be the same. This is actually a nice, easy quantity. This is not so easy. It's got a whole bunch of terms in it. So let's this. So I want to find so I guess I was ending here at part C. Okay, so let's do F composed with F. So this is F here. So I have F composed with F at X. So wherever I see an X in the formula for F, I'm going to replace X by the formula given by F. So wherever I see an X here, wherever I see an X here, I'm going to replace X by X cubed minus 3. So I'm going to replace this X here by X cubed minus 3. So let's do that. So in this formula, I'm replacing X by X cubed minus 3. And so I replace this X here by X cubed minus 3. And then I continue with what I'm doing. So it's whatever cubed minus 2. Therefore, F evaluated at F of X is just the cube of X cubed minus 2 minus 2. Again, this is a polynomial of degree 9. And so its domain is everything. Negative infinity to positive infinity. Actually, let's do this. Can I? Oh, I probably can't erase. But at least I can do that. Okay, so let's do this. So I want to do G composed with G. And so G of X is 1 minus 4X. So G composed with G at X is, wherever I see an X here, I'll replace this X by 1 minus 4X. So let's do that. Let's do 1 minus 4. And let's replace this X here by 1 minus 4X. So that is G composed with G. And so it is 1 minus 4x. Now let's find the domain. Well, the domain, let's get rid of that. Okay, the domain of